Welcome to Wireless Visionaries. In the previous video, we talked about how we can have a more directive beam and how we can change the orientation of the beam using phase shifters. So in this video, we will see how we can have more control over the beam and why we need more control over the beam. And this is because our objective is not to make a directive beam and steer the beam, but we care about the signal we have received. So particularly how much signal we get compared to the noise and interference. And these interference can come from the nearby devices or from the reflecting surfaces or the devices that operates in a nearby bands. So now let's assume that this is the pattern that we have obtained for the 8 element isotropic antenna. Potentially the main lobe is pointed towards the signal and we assume the interference is coming from the other directions. Now these side lobes have much lesser gain than the main lobe, but still the interference coming from the other directions will significantly impact the received signal. So now we need to have a way by which we can handle the gain of these side lobes. So the one way is to reduce the gain of these side lobes. And this method of reducing the gain of the side lobes is known as the gain tapering or tapered gain. So now this is the uniform pattern which we obtained for the 8 element antenna, and we fed the same signal to each of the antenna with a similar power. So now what if we want to change the gain of the outside elements? For example, the first element and the last element, if we decreases the gain of these elements, the side lobes will get diminished. And when the gain of these two elements approaches 0, this pattern converges to the 6 element antenna pattern. However, we can also choose random gain for each of the antenna elements. So when we choose random gain, the side lobes may even grow, and this can be much worse than what we have for the case of uniform gain. So therefore, we need to have an accurate way by which we can use gain tapering. So the accurate way to use gain tapering is you decrease the power of the outside elements and increase the power of the center elements. By this way, you can reduce the gain of the side lobes. So when you see this pattern that is for the 8 element obtained from gain tapering, and this is the uniform pattern. So these side lobes the gain of these side lobes is very less than the gain of the uniform pattern. But notice that now the main beam, it has got much wider than the earlier case of the uniform pattern. Choosing these combinations of gain and phase to each element is very powerful for beamforming. So like the random gain, we can also choose random phase, but this will lead to a very undesired pattern. So we are not focused on choosing the random values. So these combination of the gain and the phase, they are defined by the weight vector. So this is the illustration of the weight vector, which is given by the matrix, which is given in the matrix form. So it represents the gain and this represents the phase. So this is basically a unique representation to show what are the gain and the phase applied to each of the antenna element. So now the question is how we have to choose these weight vectors. So there are two ways by which we can choose the weight vector. First is the conventional beamformer. In the conventional beamformer, we use the tapered gain for side lobes and use phase shifts to steer the beam. So basically this is just the conventional that we have studied. Then the other way is the adaptive beamforming. In adaptive beamforming, we use optimization algorithms to adjust the weight based on the statistics of the received data. That is, we make an optimized pattern based on the environment, but subject to the constraint that we do not want to distort the signal of the main beam. So this is the main motivation behind beamforming. Thank you.